This is the first file for Math 107 for the homework over Chapter 4. So we start off with the idea of an inverse. And here's the idea is that you have this diagonal line, right? And then when you have some function here, and let me just put it as a parabola now, which might have something to do with that function. Okay, it's supposed to be a nice parabola, which you put the points together. Okay. And the inverse is as though you put this diagonal line, you folded the paper on the diagonal line and reflected the function about that line. So once you have some points for it, let's say you have 0, 7, that's a point on your parabola, in this particular parabola, then the point in the other direction would be 7, 0. Okay. And if you keep doing that with points, say you have x of 2, 11, then on the inverse you would switch those around to 11 and 2, and that's the effect of reflecting that about the diagonal line. This of course is just representative, and in this case if you go about the diagonal line you'll get something like this. Right, this is the inverse, but it is not a function. Is the line in blue a function? Yes, it would pass the vertical line test. But the one in red would not pass the vertical line test, obviously. Okay? So that's why it's not a function. But you can look at the original to see if the inverse would be a function. And if the original passes the horizontal line test, then the inverse is a function. This one did not. So when you made the inverse, it doesn't pass the vertical line test. See, when you reflect about that diagonal, horizontal lines turn into vertical ones, vertical lines turn into horizontal lines. And that's why the original function has to pass a horizontal line test in order for the inverse to pass the vertical line test. And now instead of graphing the inverse, we're going to find the inverse algebraically. And the way to do that, I'll do something else. Let's say we have another function, just want to demonstrate this, is 2x minus 9. Okay, so remember that g of x or f of x is just another name for y. So write it like this. And the first thing is switch x and y. So the y becomes an x, and the x becomes a y. Step 2, solve for y. And see what you get. Okay, so I need y isolated. So let's see, I'll have x minus 2y equals negative 9. Put the x on the other side, minus 2y equals negative x minus 9. Divide by the negative 2, fixes up all my signs, and I have y equals x over 2 plus 9 over 2. And that's the inverse. Here was the original. Here's the inverse. These are inverse problems involving exponents. In these cases, the x is up in the exponent, and you can't solve it until you get it down. Right? The way to get it down is to, and out of being an exponent, is to use logarithms. Now, in some people have probably before done things like use log 4, log to the base 7. I encourage you to only use these two logs. Use log to the base 10, which is log, and log to the base e, ln. The reason for that is those are the numbers on your calculator, the logs on your calculator, the logs that are readily available. And if you end up with something like log 4, you have to use change of base to get it to one of those anyway. So you might as well just use them. Right. And it doesn't matter which one you use as long as you're consistent. If you use, I'll show you. Alright, just want to go away. I'm going to take the log of both sides. Log of 190 equals log of 4 raised to the 3x power. Now log of 190 is a button on your calculator. Over on this side, because it's an exponent and you've taken the log of it, the exponent comes out in front. So I have 3x log 4 all multiplied together equals the log of 190. Now isolate x. So I divide by 3 log 4 on both sides. I suggest you don't do anything until you're done to this point and then evaluate it on your calculator. Could have done the same problem exactly using ln's on both sides. It'd just be ln of 4 to the 3x. 3x comes out in front. 3x ln 4 natural log of 190. Now you have to divide by 3 times the natural log of 4 on both sides. And there you go, you'll get your x. You see, it doesn't matter what you use as long as you're consistent. Now we have a case of a natural log, and we want to solve for something in the argument of natural log. In order to do that, we use its inverse, which is exponentiation. So if it's ln, I want to use e to balance it out, okay, because that will work. And I have to do the same thing on the other side, e to the 0. Don't forget that. Now e to the 0 is 1, but when I have e and natural log, they're both the same base. This side is just multiply both sides by 19x minus 12 and then solve for x. These are the rules for logarithms. I think you're probably familiar with them. If I'm taking the log of two numbers multiplied together, let's say a and b, then it can break out as a log of a plus a log of b. Just to review those rules. If I have the log of x cubed times y, that breaks out as a log of x cubed plus a log of y, taking the log of both things. And that 3 then can come out in front, so in this case you have one more step. You can't take the 3 in front until it is the exponent of everything. Here you've got the y by itself, so you can't move the 3 until you have it isolated. And if it's divided, it breaks out as subtraction. So, and if you have the log of something like x plus y squared to the 1/4 power, okay, the 1/4 comes out in front. I'll just write that as 1/4. And now I have the log of x plus y squared. I can do nothing at this point because these rules only apply when you've multiplied them or when you're dividing, but not when you're adding or subtracting. Actually, the squared is underneath that sign, so you can do nothing with it. This is, in this case, what you have to do is just carefully follow directions. And what you find is that there's a lot of new terminology that I've introduced here. You're going to use this in calculus. It can be used in other fields as well. And this term right here means that this counter in, okay, which is used several places here, as that gets bigger and bigger and bigger and bigger in the limit as it goes to infinity, because you can never get to infinity. It means as you get closer and closer and closer to infinity, this calculation will be equal to e raised to the x. In other words, the limit as n goes to infinity, that means I'm letting n get bigger and bigger, and that's what this graph is going to show you. Plus, let's use the 3. 3 over n raised to the nth power, that will be the same as e to the third. Okay, I'm going to write down here the goal. E to the third, e to the x. Okay. In the first column, when x is 3, this is like 20.08, and then it goes on and on. And when x is minus 2, it's 0.135, and then of course it goes on and on. It doesn't come out even. And when you do this calculation, as n gets bigger, you'll see that what you start with here gets closer and closer to the values that are down here. This is one way to compute e, e to the x. You might ask, how does your calculator do it? Some calculators use lookup tables and interpolate between them, but some also use some kind of algorithm, and this is one of the algorithms. Right, I'm going to erase this, and then because I need some room to write the calculation. Okay, I want to restore this. E to the x down here is 20.08. So here's how you follow these directions. First of all, in this case, I'm going to put a 3 for the x. So I've got 1 plus 3, and here's my value for n. That's n, it just didn't get written big. It's 1. So put the 1 here, raised to the first power. Well, 3 over 1 is 3, plus 1 is 4. 4 to the first power is 4. The 4 goes here. Now I go to the second step. I'm still using the 3. And now I want n to be 10. So I write the 10 here and raise it to the 10th power. This has to be done on a calculator. And this ends up being 13.8. Well, kind of round it off. So the 13.8 goes here. Now for the 100, I do 1 plus 3 over 100 and raise it to the 100th power. And when you work through that, you find that's 19.2. You say, well, we're getting closer and closer. And as you keep working this up, you'll find you get closer and closer to this answer down here, right? But you don't go beyond it. You just get closer and closer to it, and you approach it asymptotically. In this case, you have, let me erase that on the side and do a couple of these, or just show you how to set it up for the second case. It's no big deal, it just has a negative sign. It's exactly the same idea. Okay, so for the first case, for n equal 1, I have 1, well, it's minus 2 over 1, raised to the first power. Well, that becomes a negative 1 raised to the first power, which is minus 1. This starts off negative. It seems pretty hopeless. So then you try the next one, which is 1 minus 2 over 10 raised to the 10th power. Okay, so 1 minus 0.2, so I've got 0.8 here, and I raise it to the 10th power. This ends up to be a very, very small number. It's like 10 to the minus 7, so it's almost 0. Well, what's e to the minus 2 anyway? It's 0.135. So we're getting closer, but it doesn't seem like it's doing much. Let's look at the next number. 1 minus 2 over 100. Now I've let n be 100. X is still minus 2. Raised to the 100th power. And when I do that on the calculator, evaluate that on the calculator, I've got 1326. And so you can keep doing that. You'll see you get closer and closer to this number down here, and you don't exceed it, that you approach it. And this is just a demonstration of that. In 105, we spent a lot of time on exponentials and not so much time on logarithms, so I kind of hit logarithms a little harder in 107. So now you have to fill these in. Again, use your calculator. Some things you're always going to know. The log of 1, any log of 1 is 0. Okay, I've got that. Now, if x is the same as the base, then the answer is 1. So log of 10, because that's base 10, is always going to be 1. ln of e is 1. So I look through here, ln of e is 1. Here's a 10, that's 1. How about log of 100? Log of 100 is 10 squared. The 2 comes out in front. Times log of 10, which is 1. That answer is 2. Right. For the others, you have to plug them into your calculator and see what you get for answers. So this part is just practice calculating logarithms on your calculator. And then you need to graph the functions, but of course you can't put a dot at every point. Basically, logarithms look like this. Here's a y, which is some kind of logarithm, and here's your x. Right. When x is 1, they're all 0. And then they start getting bigger, but they don't get bigger very fast, but they're always kind of getting bigger. There's no asymptotic limit to the logarithm. So that's what happens for values greater than 1. For values less than 1, logarithms sort of plummet down here, getting closer and closer to minus infinity as they get closer and closer to 0. Logarithm is not defined at 0.